So we derived this waiting time, right, for a particular process or a particular customer, right. The expected time is equal to right. This is where we started off last time. Then we went through the steps of the derivation. So any questions about that and where we arrived finally, right. So one mistake which we try, sometimes we try to overuse the memoryless property, and we said that E of Ri, right, is also 1 over mu, but that is technically not correct. The E of Ri is the remaining time in service for a given customer, right, and that at any point in time the expected time for a particular customer is always, right, the expected time is 1 over mu for exponential, but this is not 1 over mu. We have to follow the same derivation whether it is exponential service time or non-exponential service time. So this E of Ri is simply E of Ri. What we derived later on is going to apply here. This cannot be approximated as 1 over mu, otherwise we will end up with incorrect derivations later on. Okay. So finally we derived our E of R, sorry, at least E of W. So what was that? Lambda E of S square divided by 2 over 1 minus rho. Right, this is what we had, and then E of T etc was, or E of R is simply this plus 1 over mu, right, all that is the same. Okay. So this is a generic expression for any kind of distribution, whether it is Poisson or exponential service time and so on. Okay. So let us look at one for exponential service time, what this reduces to. Okay. So in the case of the exponential variable, we will use again our parameter is mu, right. This is following f of x equals mu e power minus mu x, right, x greater than 0. This is our, so mu is the parameter, 1 over mu is the mean. So in this case what is the second moment? Two by mu squared, right, we derived this. So therefore you plug it in, then what do you get, right. So this E of x squared, E of s squared is the same thing, right. So therefore E of W is lambda so it's lambda into 2 mu squared 1 minus rho, there is also this 2 here. So there that becomes 1 over mu rho by 1 minus mu. Is that right, or am I missing something? So this plus 1 over mu will give you E of R, therefore, okay, right. So that is how this can be used. So now we come to our special case, right. So we look at a deterministic service time. Right. So how will you define the deterministic service time? Let us say that the service time is fixed as 1 over mu, right. There is only one value for service time, all packets are fixed length, right. So all packets are all customer service time, right. So therefore that is right. So the E of s is simply 1 over mu, it is a constant, right, there is no variation in the service time. and what is E of S squared now? E of S squared is simply square, right? It's so the all possible values, but there is only one thing, simply 1 over mu squared. There is only one possible value, and that's with probability 1. What's E of x squared? For every value, f of x equals x into probability of x, right? In this case, the f is simply x squared, right? X squared into probability of x. X takes the value 1 over mu, for 1 over mu squared into only probability is 1, right? So this is from basic principles, right? There is nothing. So therefore, your E of w is now lambda 1 by 2 mu squared 1 minus rho. So that now becomes 1 over 2 mu into okay. So this is basically the formula for this is the MD1 Q, right? This is. So MD1 occurs whenever you have fixed length packets, for example. In ATM switch, all packets are fixed length. So then what is the delay in an ATM switch? Okay. So E of W is this, and E of R is simply 1 over mu plus okay. So the special thing about MD1 is that is the one that distribution is given that Poisson arrivals are there, only for MD1 will you have the least waiting time. The waiting time is least in the case of MD1Q. How do we prove that? From this expression. Previously we saw for Poisson it is rho by mu into 1 minus rho. In this case rho by 2 mu into 1 minus rho. Why can't I go below that, or at least mathematically, right? Let's look at intuition first. Mathematically, how do you show that you cannot do any better than that? Okay. So another way to do that is to look at the coefficient of variation, right? So we can define the same thing in terms of COV, and then we can show that CS equals that COV equals 0 only for MD1. For no other distribution is COV going to be equal to 0. Okay. So okay. So let's look at that. So if you look at Raj Jain's book, they will have it in terms of the CS expression. That's why I'm kind of deriving that, right? So E of S squared, let us try to define this in some other way. Okay. So first let sigma s, right, denote the standard deviation of service time, right. So therefore the variance in S is simply sigma squared. Then we will define this thing called coefficient of variation. We will define this by CS is the ratio of by mean E of S, right. So E of S is the mean and sigma is the very standard deviation. So the ratio of standard deviation to mean is your coefficient of variation. So therefore your CS squared is equal to so now we need to connect our variance with this CS squared or with that E of S squared, right. So variance of S is also equal to what? Another way of defining is E of S squared minus S whole square. okay, let us take this one step further. So variance of S is also sigma square, right. Squared. And sigma squared is equal to what? Here somehow, right. So let us bring the CS squared definition. So it is basically CS squared into EFS whole square, right. So it is CS squared into EFS so all in all we get this thing 1 plus that is my EF square, right. So therefore EFW, the generic expression that we derive, is now simply up. Yeah. I am just plugging in our EFS squared with this term, that is all, which we know, right. So EFS squared, which was there in the earlier formula, is now replaced by this, which I can rewrite. So lambda ES is what? Lambda into EF. Lambda is the arrival rate into service time is simply the utilization, right, rho. So lambda ES is rho. So this is rho EFS 1 plus CS squared divided by 2. That is the formula in Rajain's book, which expresses that in terms of the coefficient of variation. Questions on this so far? None? So now we can say that so coefficient of variation is going to be 0, right, only if the variable is constant. Only for MD1, for the deterministic service time alone, CS is going to be 0, right, and therefore that is going to be the least. Anything else will have greater than 1, greater than 0, right. So for exponential service time, exponential service time distribution, what is CFS? CF is the ratio of the variance to the mean, sorry, a standard deviation to the mean, right. In the case of so in the case of Poisson, the variance equals mean. In the case of exponential, the standard deviation equals mean. Right, because E of S squared is 2 by mu squared minus 1 by mu squared, therefore variation equals 1 by mu squared, right. For exponential variance is 1 by mu squared. Again, if we go back to our definition, some things you have to go back and figure it out, and therefore standard deviation is 1 by mu. So therefore this is the only case for which CS equals 1, and then of course so 1 plus 1 by 2, and then that formula will apply, right. So for deterministic service time, what is standard deviation variable having single value? 0. So therefore the waiting time is the least, and the service time is independent, right. Service time is independent of the waiting time, because that is always dependent on the server's capacity. So therefore the least delay, overall delay, not only waiting delay, the least overall delay will also be seen for a given m/x/1 distribution. The least total delay will be for the MD1 system, everything else will be more than that, right. So therefore and the convenient thing is if the waiting time in the case of exponential is twice that of the deterministic, that is also sometimes useful. So if you suddenly see a 2-mark question that tells you MD1 system, this is the delay, waiting time is 2 milliseconds, tell me the delay for the other one, then you should know that I simply have to multiply this by 2 and I'm done, and calculate mu if you have to. Okay, so that is the MG1 derivation. Okay. Questions? Questions? All right. So now we will look at this one variation, right? One can go on endlessly on this MQ system. You can go to MG1, then GM1, and so on. But we will probably stop with this MG1 for the single queue systems, because I want to get into queues of networks or networks of queues, whichever. So now we will look at a system with MG1 with vacations, and there are applications for this. It is not a made up thing just to satisfy some professor's curiosity or some PhD student's curiosity here, right? Saying, why don't you do some vacations and see what happens? There are legitimate applications of this. Okay, so the definition of vacation in this particular derivation that we are going to look at is whenever the system is idle, right? When there is no customer to be served in the queue, the server goes on vacation. That is all. When the server comes back from vacation, if the queue is still idle, it again goes on vacation. So that is, so the vacation time itself is a random variable with some distribution, right? So that could be either deterministic or exponential or whatever it is, right? So there is some distribution for the vacation period, but this is the definition of vacation. Vacation is what, when you sometimes you go to the bank, right? There is already 3 people in the queue, but still that guy will go for a break, right? That is not the vacation. Here the idea is that the queue should be idle for the server to take a vacation. So in terms of where this would be applicable is if you are thinking of say a machine, right, on a machine which you are, your lathe or whatever it is that you are using it for some jobs, then whenever there are no jobs to be done, you simply take down the machine for maintenance. It's a vacation that simply means maintenance period where you will do some maintenance or some mundane activities and so on. Or if it is in the case of networks, you might say I will want to do some control packets or some sort of maintenance information has to be sent. You want to wait until the queue is empty of all data packets before you send some of these control packets, right, specifically for diagnostics purpose or something like that. So that is where this vacations will be applicable. Okay.
Do we consider that the moment a new packet has come, at that very moment this vacation ends?
No, that is not. Only when the server comes back will the vacation. So when a packet comes to a queue which is empty and the server is on vacation, the packet has to wait until the server comes back from vacation.
Okay. The only thing is that at the time of starting of vacation is limited by the queue being empty.
Yeah. When the queue is empty, but when the customer
end of vacation is not.
End of vacation is no. Where end of vacation you find the queue still empty, you can again go on vacation. If there is a customer waiting at the end of vacation, you have to serve the customer. And the customer that comes to a server on vacation has to wait until the server comes back, right? You won't want the server does not, it's a maintenance routine, then the server that cannot be stopped. So there is some waiting time as far as the customer is concerned, even if it comes to an empty queue. That is the difference between this one and the previous model.
Server going on vacation can be in any of the queues, like right MM1 queue.
This is only MG1.
But it can, a server can go on vacation in case of MM1
other
also.
Types also. Yes. Our analysis is only for MG1. Yeah. In any, if it's MMM, it's a little bit more complicated because the server can go, but there are M-1 servers in the system, right? And of course now in that case, if I look at a shared queue, then only if the queue is empty, right? There is nobody, no packet in the queue, then all servers can go on vacation.
But in case of MM1, it will be the single queue is there. So
MM single queue, single server. When the queue is idle, server takes a vacation. That's the definition.
So what would be the effect in the waiting time? Because
this will be added.
So this will be added.
This will be, yeah. So your residual waiting time will depend upon not only the service time of the packets in front of you, but also the vacation time of the server itself.
The residual time of the vacation
Yeah, that's the same thing. Same derivation will apply now. So if I come to an empty queue and the server is on vacation, the residual waiting time, residual vacation time is what will be. So from a user perspective, coming to an idle queue is as good as there is one customer in front of you who is being serviced. Whether it's right, theoretically there is no service, but is also waiting for the server to come back after finishing some other job, or in this case just maintenance or vacation. So let us write this down, right. So when the queue is empty, the server goes on vacation and returns. If customer is waiting, when the server returns, then this customer is serviced, right, then service starts. Else server takes a vacation again. And then returns after some time. So let V be the random variable representing the vacation time. So the R now also includes vacation time. So that original derivation for W, that does not change, right. So E of R that we saw includes the vacation time, because from the user's perspective it does not matter whether its server is busy with another customer or simply not available because it is on vacation, right. Packets are simply queued, this is infinite queue, so all arriving packets will be queued. So there is going to be no service drop in this particular case, you just wait there until the server gets back to starting servicing packets, right.
So in this case, can we say that we are modeling the server with a dummy process, like if it finds the queue empty, it generates a dummy customer and services that.
That's, yeah, is as good as that, yeah. Only thing is the vacation time distribution is different from the service time distribution, right. So that can be different, that could be longer, for example, it could be, say, on average it takes 10 minutes to service a system, to maintain a system, right. That is different from the service time distribution. So this equation still holds, E of W is still equal to E of R by 1 minus rho. Only thing is I have to also compute my E of R differently. So if you look at the picture, yes, it is similar to what you are saying, that it is no different from yet another customer who is sitting in the queue, okay. So we will use the same notation, this is that R of tau, and this is tau, and this is time 0. Oh. So this is 0, this is some time t, okay. So this is the service 1, right, service 2, then service 3. And now let us try different color. That is vacation. Maybe I should choose something. Okay, that is one V. If you want, we will draw one more V, though this is getting to be, it is actually highlighter setting. I am not changing the pen color, so it is kind of coming weirdly like that. And then you have your regular service, right. So this is S4, this is V1, this is V2. This just to show that in case the server comes back and the system is still empty, then it will continue taking vacation, right. And this packet 4 could have arrived anywhere, not in between during the second vacation it would have arrived, right, somewhere here your packet 4 arrives. So now again my expected value of the residual time, mean residual time, is given by 1 over t 0 to t r tau d tau okay. So we will use the term m of t to denote the number of completions like last time, we will use the term L of t. So L of t is the number of vacations during this period. Is the number of completions. Okay. So what do we have now? What's it going to be? Simply last time it was 1 over sigma x squared, right, or sigma s squared. In this case it is going to be sigma s squared plus sigma v squared, right. Again this height is v1, this width is also v1. So therefore this is equal to by 2t, it is always there. I goes from 1 to m of t. So the first half of that we already derived last time, that is simply lambda xi squared x or lambda E of s squared by 2. Or did I say x? Sorry, that should be s. Right, so E of by 2 is and then we remember we did the mt by t, and so mt by t was lambda, right. That is how we did it last time. Say we added multiply divided by m of t and then we got the derivation. So I hope you remember that. So if I simply say that this is equal to lambda by 2. So then let us again do that L of t by t, okay. Then this would be sigma vi squared over all the v's divided by L of t. There is again 2 here. So multiply divided by L of t like we did before. This was the term, right, vi squared by 2t was there, we simply added this extra term. So what is vi squared by L of t? E of v squared, right, second moment of vacation time. So this is so sigma vi squared from 1 to L of t divided by L of t is nothing but the second moment of the vacation time. Now what is L of t by t? So L of t by L of t is the number of vacations taken in time t. So this is the average number of vacations, but somehow we do not have, in that case we got it as lambda. So that is the number of service completions was equal to the arrival rate, therefore that was m of t by t is little bit easier. So the L of t by t, one extra work is, a little bit of work is required, okay. So let us look at it this way, right, what is the total time spent by the server vacationing in some interval 0 to t, what is the total time spent? You can look at it two different ways.
Probability of it being empty is what we are looking
Yeah,
at.
so what is the probability of the queue being empty?
In a time span of 0
in the
to
time span, right, okay. So therefore that is simply, so what is the, okay, so the duration, total duration of vacation, right, is the total duration. This is given by make sense. What is the server utilization? Rho, right, and when rho is less than 1, that is also the fraction that the server is busy, and 1 minus rho, remember, is p naught, fraction that the server is idle, right. So p naught into t, that is the total time that you would expect the server to take vacation on average, right, this is again average. So 1 minus rho into t is one way that I can derive the total time the server was on vacation, agreed. Another way, this is also equal to it's also equal to something else. The number of vacations taken into average time per vacation, right. So I can look at it both ways. It is simply that in the given interval it took 4 vacations, each vacation was of 10 minutes average, therefore the total average time taken, right. So this is with respect to the in the interval 0 t, right, this is what we are trying to equate. So therefore we vacate these two fellows, right, equating. So LT by T in the long run approaches one minus rho by E of V. Right. LT into V of V equals T into 1 minus rho, therefore LT by T approaches 1 minus rho divided by E of V. Questions on this part? Yeah.
Like what if the customer comes when he's already on vacation?
When customer comes when he is on vacation, when the server, okay. That is true, yeah. So if when the server is on vacation and somebody arrives, yes. So there is an approximation that we are trying to take. Yeah. So in that case the queue is technically not empty, but at the instant that the server went on vacation the queue was empty, right. So therefore that's the, yeah, that is an approximation there. So therefore our EFW now translates to lambda because there is 1 minus rho on top, right. Remember your EFW equals, I was straight away gone to EFW. EFR has EFR divided by 1 minus rho is our EFW, right. So I have skipped one step in the derivation. If we complete our EFR is lambda ES squared divided by 2 plus 1 minus rho by 2 EFV into EFV squared. So 1 minus rho factor vanishes when I divide that, when I bring in EFW equation into consideration. Maybe they should reboot பண்ணுமா system, twice it keeps doing. So this is our derived expression, right. So that's what our EFR translates to. We divide this by 1 minus rho to get this above expression. Okay, so now I have MG1 with vacations. So if I want to plug whatever I want, so if it's MM1 with vacations, no big deal. I only need to take my MM1 delay plus the server's vacation time. So as long as you know the first and second moments of the server's vacation time, I am done. I can get the mean, right, not other parameters, but the mean of the service time I can get with vacation. Questions? Okay. So the best application, or at least one easy application that we can relate to, is a TDM system. All remember we did slaughter log earlier on, right. Now you look at, let's say I want to model time division multiplexing, right. So time division multiplexing is defined as you have a set of n users who want to share a medium, single medium that is being shared. Instead of Aloha you use TDM. Idea is that for every user there is a slot, and therefore, right, so what is the average delay of TDM that a user will see. So every user has a queue, right, and then the queue, whenever the user gets his or her slot, then you send a packet. But once you send a packet, the server uses you again after m-1 time units, right. So technically, or m units, technically you are seeing the server's vacation time as m. So that is how we will try to model the TDM system as mg1 with vacations and see if we can get that done correctly. Okay.
But in this case, if we have a deterministic vacation distribution,
Mm-hmm.
this will become 0.
E of v squared won't be 0, only E of v squared will simply be vacation squared, that is all, m squared by 2m, that is what it will be, right. Again, remember the second moment does not go to 0, only the standard deviation goes to 0 for deterministic systems.
So here the response time we still can calculate as E of w plus 1 by mu.
1 by, yeah, because that is the service time, right.
But there is still vacation period.
No, after the server comes to you is when you are right. So this is E of r includes the time that you spend waiting for the server also to come. Waiting for the server is as good as the server serving somebody else, right. So your E of r, so once my waiting time is over, all I do is wait for my service. That is still right in the case of mm1, or it is E of w plus E of s, if it is here mg, right. So that is why we have included the service time in the residual service time also includes the server's vacation. So here is one standard multiplexing problem. We see this in wireless networks, right. Wireless networks, you have a large bandwidth, right, say 20 or say 200 megahertz bandwidth is available, that is what you paid for in auction or whatever it is, right, and you want to service your customers. So then let us say you know that the number of customers is fixed, right, so only 20 customers are there, you have 200 megahertz of bandwidth. Then the two choices are, or three choices are there, right. So how do you effectively share this? One is to break down the 200 megahertz into 10 megahertz chunks and give each user 1/20th of the total bandwidth, right. So what is that system called? FDM, right, frequency division multiplexing is where you simply share the bandwidth equally. So everybody has their, you break it into subchannels, m subchannels, every user has their own subchannel. Only thing is the capacity of that each subchannel is a share of the total subchannel, right. So let us try to do that comparison here and see what kind of system there will be. So FDM versus TDM, okay. So you view the channel itself as a server, right. If you look at a single user, each user has a queue and then they are going to have a corresponding server, right. So if I were to, so here let us define the system first. So there are m, right, Poisson traffic generating users, okay, and the channel bandwidth, channel is divided into, so when I say channel, it is the entire capacity that you have paid for, that you own 200 megahertz, you can use it however you want, right, is divided into m subchannels of equal capacity. So that what is the disadvantage of FDM is that if I send a packet, it is going to take m times longer. When I have 200 megahertz, right, and I have only 10 megahertz channel, my bitrate is proportional to my bandwidth. So therefore larger the bandwidth, higher my bitrate, higher the bitrate, less the time it is going to take, right. So the service time will be longer in the case of FDM because I only have 1/m of the total bandwidth, right. So it will take m times the time to send with the entire capacity was available to me. Agreed? Agreed or not? Yes? If I have 200 megahertz, let us say I do 1 bit per hertz, I get 200 megabits per second, right. I have 1 kilobit packet, it will take me 1 kilobit by 200 megabits is the time taken. But I break it down to 20 users, each gets only 10 megahertz, then I get 10 Mbps. So 10 Mbps will take longer compared to 200 Mbps channel, that is all, right. So therefore the service time will be, only thing is I get the channel entirely to myself, right, my subchannel is entirely, right, and each user is given a So this FDM versus TDM debate has been around for a long time. Even today our cellular systems, right, some of them are FDM. What does GSM have? For those who read WCN, what does GSM do? FDM, TDM or something else? It's actually hybrid, both FDM and TDM. FDM, TDM, right? So you have FDM and then you have slots within each frequency, but you have this notion of a frequency and then that is time shared. That is the next step, right? So initially it was simply FDM or TDMs. Then of course CDMA came along, Qualcomm, right? So that is a different thing. You use the whole spectrum, but you are using codes to let them act or send simultaneously, but you differentiate. But there is, you are still having complete access to the entire spectrum, right? So that is your FDM, right? So this is our FDM definition. And then let us assume that each user's the Poisson, right, per user is, just to make life simple, it is lambda by m packets per second, right, or lambda by m units per second. Assume that all are fixed length packets, right. So as I said, fixed length packets. Okay, and this is fixed length packet of which takes 1 unit given the complete channel capacity. That is my definition of unit. Yeah, full 200 megahertz, right. So that is so we will write this for the sake of, so example 200 megahertz, which is broken down into we said 20 channels of 10 megahertz each. That's our example. Okay. So this is lambda by n, right, packets per unit time. That's our this thing. Okay. So now how do we model the system? What kind of queuing model will be applicable here? How many servers are there? How many queues are there? There are m servers, right? Every subchannel is a server, and there are m queues. So this is what we saw before, right? So there is m separate queues, and each queue has its own server of capacity. This, right? Okay. So what is the time? What is the capacity of this server itself? It will be 1 by m. Capacity of each server is 1 by m, right? Mu is equal to 1 by m. Okay. All right. So I have C1 to Cm. There is a corresponding queue for every user, and here packets are arriving at the rate. So the capacity here, so mu is 1 by m, 1 packet every m units. The book is cut. Okay, let us forget the book for now. Let us see what this is.
We can call it m times mm1.
Yeah, this is m separate. Actually, since I said fixed length packets, this is each of this is an MD1 queue. Yeah, the independent queue. So right, this is it. And
why will arrival rate be lambda by n?
that is because I am just assuming the total. This is a convenience assumption. The total rate is lambda, and each user is generating at rate lambda by m. I could have made it lambda per user and said m lambda. That is also, but just assuming that all of them are generating at the same rate, and the total rate is the sum of all their rates. Right? Yeah, that is all. So that lambda by m is just for the sake of convenience. That is all. Because I am looking at the total offered rate to the system is what we sometimes know. What is the total capacity that the system is expected to serve? You use that as lambda, and then you are saying that it is equally, right. Each of these guys are generating their equal share of the total load. Okay. So now this is right, so each queue is modeled as an MD1 queue. So therefore that let us define rho. So rho is rho equals lambda, right, lambda by m by 1 by m, therefore that equals lambda. Each user, right, each queue has lambda by m arrivals and 1 by m service, right, because it takes m units to service a packet, therefore per m, yeah, so each unit, each time unit you are serving 1/m of a packet. Let us say so what is that, rho divided by 2 mu into 1 minus rho, right, that is the waiting time. So therefore rho is this divided by 2 and mu is 1 by m, right, so therefore this will be 1 by m 1 minus rho. Given lambda, now that is why we do this lambda, right, I know lambda, I know m, I can simply say that this is the expected waiting time, and what is the expected service time, total response time, plus service time is m units. So that is our derivation there. Okay, so that was simple enough. Right. Independent queues, no, therefore the delays are all independent, there is nothing common there. Questions? None. Okay, now our TDM system. So the TDM system is modeled as follows. Okay. So there are m users, so 1 to m. Oh, I do too many lines. Okay, you don't need to draw as many lines. Can make a difference. Okay, so 1 to m, that m is so badly visible. One to m users. Okay. Now is it separate queues or combined queue for TDM? Each user is again generating traffic at rate lambda by m, right? So therefore it is again separate queues only, right? So this is user I. But the channel is modeled slightly differently. Okay. Again it is a single server system, again it is MD1, so there is one server, service time is fixed because the slots are fixed length, right, and it is MD1. Well, the only problem is if a packet comes to this queue, right, this queue is let us say empty currently, the queue is empty, right, and just after 1 plus the first slot is starting at time 1, right, at 1 plus epsilon a packet comes to the queue. So technically the queue goes off on vacation, right, how long does it go for vacation? It goes for m time units because your next slot is only 1 unit away, right. So that is one. The service time, what is the service time? The service time for each packet is also m time units, right, because the guy in front of you, so there is one packet in front of you, he gets serviced here, when will you get the service? server next after m time units, right. So you get the server every m time units, that is one definition, therefore the service time is again m time units, right. So therefore your mu is again 1 by m, okay, but there is this unfortunate part that even if you come to an empty queue, right, you won't get serviced right away. If you come to the empty queue, the server has gone on vacation, basically it has gone to the other m minus 1 users, right. So this is an MD1 with vacations.
The main concept that where the complete server is available, or in this case the complete bandwidth is available for that time, that doesn't make any difference.
That will come next, that will come when we do the service time. The actual packet transmission time is only 1, but the time between two consecutive packets is actually m. So from this user's perspective, I am getting the server once every m slots, right, but when we do the EFR, it will be that plus 1, there it will not be plus m, there will be plus 1, that will be the difference there. So EFW will not see the fact that each packet only takes one time unit, only in terms of waiting it, each packet ahead of you takes m time units, because that is how often you see the server. So rho is again lambda, so now the vacation, right, so EF v squared, vacation is again fixed time, right, it is always m units, every time if you miss the server it goes off and services somebody else. So EF v squared is m squared, EF v is m, right, fixed. So therefore EFW is basically rho by 2 mu into 1 minus rho. So rho is lambda, mu is again 1 by m plus, so the waiting time here is more than the waiting time of, the mean waiting time is higher in the case of TDM, because even if you come, whereas in the case of FDM you come to your empty queue, your channel is always there, your server is always there to serve you, right. So that is what this that difference is what you would see here. So this is m lambda 2 into, so when lambda is small, well regardless of the value of lambda, right, the average waiting time is always going to be higher in the case of in TDM system, okay. So this is E TDM. And the response time is the waiting time plus 1, yeah, because you do not need m, in the previous case it was m, in this case it is only 1, and 1 time slot you are done. So that is all that you have. Now I can actually simplify this, can't I? Yeah.
You are like technically putting u as 1 by m to denote that if I transmit in a slot now, only after m slots I can again transmit another thing.
Yeah, yeah, that's correct.
And you're also modeling vacations.
Vacations, yes. So say look at one packet's perspective, right? I am the I have one packet in front of me, right? And okay, so that packet has just now started service, right? When will I see the server next? After m time units. So the time between two consecutive packets getting serviced at a given queue is m, that is why your service rate is 1 by m. The actual transmission time is only one slot you are done, right, whereas in the case of FDM you needed m slots to actually send the packet because your bandwidth is divided, right. Here you are having 200 megahertz channel, it is divided in time, there is divided in frequency, that is why. So if you want we can simplify this further to m by 2 into 1 minus lambda. And now which is better, TDM or which will always have lower total response time? So if we simply compare, one had E of W, this one had E of W plus m by 2, that had E of W plus m, right? This had E of W of the TDM plus m by 2, but this is 1, therefore the difference is simply m by 2 minus 1. So if you want to write that, E of R TDM is E of R FDM minus so therefore it will always be yes. In the case of TDM,
If there are two arrivals that are very close to each other, and then even when the queue is not empty, it will go for vacation time.
Even if the two arrivals close to each other, you mean? Okay.
Go to vacation time.
Even when if you miss your slot, the server goes on vacation. That's what the implication is, right? If you had arrived, if there was a packet in the queue at the beginning of that slot that is allotted to you, then the server cannot go on vacation. That server serves the packet. So even if two packets come just after the slot has started, the server comes and checks the queue, it is empty, it goes off, because it cannot start transmission after the slot, after that period, right? If two arrivals come before the slot, then that is fine. One of them will get serviced, right? When the server arrives. After that server will only come back after m time units. Server will not serve two packets at a time, only one packet at a time. That is a different system. That will be MG1 reservations and things like that, right? Here is only one packet serviced at a time. If you do reservation system also, we can do analysis, right, where you will reserve multiple packets, where more than one packet can be transmitted. That is with reservations you will try to do, right? But in this case, that's the thing.
Sir, it should be m by 2 plus 1. Because m by 2 is also adding, then 1 is also adding.
Sure. There is a plus m by, there is a, so see what you have is, here you have plus m, here you have plus m by 2, and then you have plus, this is m by 2 plus 1 is here, there you have plus m, right? So it is m minus
EW of TDM is m lambda
yeah, okay.
plus m by 2.
So we will do this.
M by 2 is extra here and 1 is extra here.
Plus this is m by 2 plus 1 on this side, and here you have plus m here, right? The rest of the term is common. The other term, only these two are different, right? Other two terms are the same. So it will be, there is m minus 2 and then yeah. Wait a minute. No, that term is going to be the same. We simplified this to m by 2 into 1 minus lambda. The two terms, so there is m by 2 here, right? This m lambda by 2 m 1 minus lambda is the same for both, right? There is m by 2 plus 1 here, and there is plus m there, right? So therefore this is equal to, yeah, so I am going to bring this fellow this side, okay. So this shows that in the long run, right, as or in general, even though the waiting time is slightly higher, the service time will make a difference. So if your m is very large, then your improvement will be better. If m is very small, then it is not much, right? If m equals 2, that is, what is the difference? 2 by 2 minus 1, so 0, right? If only 2 channels, 2 users, it does not make a difference. When you go to more than 2 users, it makes a difference.